For millennia, humanity gazed at the stars with wonder. We crafted stories about the cosmos, yet it was Albert Einstein who truly revolutionized our understanding of the universe. In 1915 he unveiled his theory of general relativity, changing our perception of gravity. He proposed that gravity wasn't a force but a consequence of the shape of spacetime itself. Matter warps spacetime, and this warping is what we experience as gravity. Einstein's theory of general relativity was a radical departure from the Newtonian understanding of gravity. Newton described gravity as a force acting at a distance between objects with mass. The Earth pulls on the apple, the sun pulls on the Earth, and so on. But Einstein saw something deeper, something more profound. He proposed that gravity wasn't a force in the conventional sense. Instead, it was a manifestation of the curvature of spacetime itself. Imagine spacetime as a vast, four-dimensional fabric. This fabric is not some ethereal, intangible entity. It is the very essence of the universe, the stage upon which the cosmic drama unfolds. Massive objects like stars and planets distort this fabric, causing it to curve. Picture a bowling ball resting on a stretched rubber sheet. The weight of the bowling ball causes the sheet to sag, creating a depression around it. This is analogous to how mass warps the fabric of spacetime. Now, imagine rolling a marble across the rubber sheet. As the marble approaches the bowling ball, it doesn't travel in a straight line. Instead, its path curves as it follows the contours of the warped sheet. In a similar way, objects moving through spacetime follow the curvature caused by massive objects. To grasp Einstein's revolution, we need to expand our understanding of the universe. We're accustomed to thinking of space and time as separate entities, space being the three dimensions in which we move, and time being the relentless flow from past to future. But Einstein shattered this classical view. He showed us that space and time are inextricably linked, woven together to form a four-dimensional fabric called spacetime. This fabric is not some static backdrop, it's an active participant in the cosmic dance. It can stretch, warp, and ripple. Imagine a loaf of bread representing the fabric of spacetime. Each slice represents a moment in time. Now imagine a marble placed on the loaf. The marble's weight causes a slight indentation in the bread. This indentation represents the curvature of spacetime caused by the marble's mass. As the marble moves across the loaf, it creates a track through the slices, representing its journey through both space and time. This interconnectedness of space and time is fundamental to general relativity. It's not just that mass affects time, or that time affects space, rather, they are two sides of the same coin, forever entwined. The more massive an object, the more it distorts the fabric of spacetime. Think back to our trampoline analogy. A bowling ball creates a much deeper sag than a golf ball. Similarly, a star warps spacetime far more dramatically than a planet. This warping of spacetime is what we experience as gravity. The Earth orbits the Sun not because of some invisible force pulling it inward, but because it follows the curvature of spacetime created by the Sun's immense mass. It's like a cosmic roller coaster, with the Earth perpetually riding the dips and curves carved out by the Sun's gravitational influence. Even light, which travels at the fastest speed possible, is not immune to the effects of spacetime curvature. As light passes by a massive object, its path bends slightly. This phenomenon, known as gravitational lensing, has been observed countless times, providing further confirmation of Einstein's theory. Section 5. Cosmic plunges, black holes and neutron stars. In the vast expanse of the cosmos, there exist objects of unimaginable density and gravitational pull, black holes and neutron stars. These celestial behemoths are born from the death throes of massive stars, their cores collapsing under their own immense gravity. Black holes represent the ultimate victory of gravity over matter. When a sufficiently massive star exhausts its nuclear fuel, its core implodes, crushing itself into an infinitely small point called a singularity. The singularity's gravitational pull is so intense that nothing, not even light, can escape its clutches. Neutron stars, while not as extreme as black holes, are equally fascinating. These stellar remnants are composed almost entirely of neutrons, subatomic particles packed together with incredible density. Imagine squeezing the mass of the Sun into a sphere the size of a city. Both black holes and neutron stars warp spacetime to an extraordinary degree. Their gravitational influence is so powerful that they create regions of spacetime where the normal laws of physics break down. Studying these extreme environments allows us to probe the very limits of our understanding of the universe. Section 6. Bending light's path, gravitational lensing. Einstein's theory of general relativity predicted that gravity could bend the path of light. This phenomenon, known as gravitational lensing, occurs when light from a distant object passes by a massive object, such as a galaxy or a cluster of galaxies. The massive object acts like a cosmic lens, bending and distorting the light from the more distant object behind it. This can create multiple images of the background object, or even smear it out into arcs or rings. Imagine holding a magnifying glass in front of a candle. The lens bends the light, creating a magnified and distorted image of the flame. Gravitational lensing is a powerful tool for astronomers. It allows them to study distant objects that would otherwise be too faint to see. By analyzing the distorted images, astronomers can learn about the mass and distribution of matter in the lensing object, providing insights into the structure and evolution of galaxies and clusters of galaxies. Section 7. Einstein's triumph. The 1919 eclipse. Einstein's theory of general relativity, while elegant and groundbreaking, needed observational evidence to be taken seriously by the scientific community. The perfect opportunity arose in 1919, during a total solar eclipse. Einstein had predicted that the sun's gravity would bend the light from distant stars as it passed by. During a total solar eclipse, the moon blocks out the sun's blinding light, making it possible to observe stars that appear close to the sun's limb. British astronomer Arthur Eddington led an expedition to observe the eclipse from two locations, one in Brazil and one on the island of Principe, off the coast of Africa. Eddington's team carefully measured the positions of stars near the sun's limb and compared them to their positions when the sun was not in the way. The results were astounding. The stars appeared to have shifted slightly from their expected positions, precisely as Einstein's theory predicted. The amount of shift matched Einstein's calculations with remarkable accuracy. Eddington's observations made headlines around the world, catapulting Einstein to international fame and cementing general relativity as a cornerstone of modern physics. Section 8. Spacetime in action, from GPS to gravitational waves. Einstein's theory of general relativity is not just an abstract concept confined to textbooks and academic discussions. It has real-world applications that impact our daily lives. One of the most notable examples is the Global Positioning System, or GPS. GPS satellites orbit the Earth at high speeds and rely on precise timekeeping to determine your location on the ground. However, Einstein's theory tells us that time slows down in stronger gravitational fields. Since the satellites are farther from Earth's gravity than we are, time moves slightly faster for them. To compensate for this relativistic time dilation, GPS satellites have built-in atomic clocks that are precisely synchronized with clocks on Earth. Without these adjustments, GPS navigation would be inaccurate by several miles each day. Another fascinating prediction of general relativity is the existence of gravitational waves. These are ripples in the fabric of spacetime caused by the acceleration of massive objects such as black holes or neutron stars orbiting each other. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by directly detecting gravitational waves for the first time. This groundbreaking discovery opened a new window into the universe, allowing us to study some of the most violent and energetic events in the cosmos. Section 9. Unraveling the Cosmos, the Future of Spacetime. Einstein's theory of general relativity has revolutionized our understanding of gravity and the universe. It has provided us with a framework for understanding the evolution of the cosmos, the behavior of black holes and neutron stars, and the existence of gravitational waves. However, despite its successes, general relativity is not the final word on gravity. It is incompatible with quantum mechanics, the other pillar of modern physics that governs the microscopic world. Reconciling these two fundamental theories is one of the greatest challenges facing physics today. The quest to understand space-time continues. Physicists are exploring new theoretical frameworks such as string theory and loop quantum gravity, in an attempt to unify general relativity and quantum mechanics. These theories propose radical new concepts such as extra dimensions and quantized space-time, which could revolutionize our understanding of the universe once again. The future of spacetime research is bright with promise. From unraveling the mysteries of dark matter and dark energy to detecting gravitational waves from the early universe, the coming decades are sure to bring exciting new discoveries that will further illuminate the fabric of the cosmos.